PostgreSQL has become the most popular database in the past 2 years. This led to a lot of attention to the Postgres open source community, which led to funding, which led to a lot of companies, SaaS companies with Postgres offering. And eventually it's a good thing for the Postgres community, because this brings funding, eyes, developers, people with interest to the Postgres, and what we get as a result is improvement, because that's what all we want to improve this product, right? And one of the very beautiful improvement that happened in the Postgres 17, which is not released yet, is still in beta, is combined IO or vectorized IO. You see, I want to talk about this in general, but to kind of give a summary before we jump into this, the meat of this podcast is Postgres today work with pages like every database out there, right? You have the fixed size pages, and this pages is, these are just a hunk of bytes for indexes, for tables, for pretty much anything, even transaction logs are worked with pages, or fixed size pages. It's just easier to work with, fixed size pages as opposed to variable size. And these pages are 8 kilobyte in size. So when I want to read a concept of a row or an index, it eventually turned into a page read, or they call it block read. Block is very overloaded term. I keep saying this because block shows up everywhere in this stack, in the kernel, in Postgres, in the database layer, in the kernel itself, block layer. There is the block sizes in the SSD itself. So I try to kind of use different terminology, but I might get yelled at when I do that. So there is a page. There's this page fixed size, right? And Postgres today reads, when it reads a page, it reads just a single page, and it sends that command to the kernel to do the read from disk. That is, if that page is not available in memory, in the shared pool buffer, because we always do caching for these pages. It's just easier this way, right? So the improvement becomes in that read. So a system call, which is a read, pread, it's called, to specify the position as well. Like, hey, I want to read that. It gets translated to a normal read like you and I do when you read from file. What do? You specify, hey, where in the position and how much bytes you want. That's what a read is, right? So this will be translated to, read from position 10,803 for 8 kilobytes. Always like that, 8 kilobytes, right? And that's where you get back a page. So you see, this is kind of inefficient in a cases where the planner did a sequential scan, right? I'm just reading the table, right? I'm doing a full table scan. I stop when you get 3 rows, right? Something like that. Or stop when you find these matches. That's what you do, right? It's sequential scan. Or even index scan in case you're doing range scans. These are very beautiful, nicely tucked in, because the B plus tree structure, the leaf trees are linked to each other. And if you read something sequentially, and let's say you don't go back to the heap, you just read what the index has, this is also a kind of a sequential read. It doesn't have to be a full table scan. So you see that we know the next page. Right? I'm getting this page 1, then page 2, then page 3. And this today translate to read, as opposed to one read for, 3 pages. Today, if you want to read 3 pages, these are 3 system calls. Right? Read for 8 kilobyte each. But with combined IO, they predict, we're doing a sequential scan. Probably we're going to need 7 pages or 5 pages or 3 pages. So let's just send one system call to the kernel saying, hey, I just want read from positions 700 for 8 kilobyte times 3. Do you see the idea? That's all what it is, you know, just combined IO, vectorized IO. And they don't have to be even sequential, you know. There is another system called pread v, which stands for vectorize. Pread v stands for vectorize, takes an offset where you want to start the reading, and it also takes an array of buffers, which basically where do you want to store these pages. So you will tell, hey, read first 8K, put it in this buffer as a user space. Read the second one and put it in the second buffer. Read the third one. So this way, one read, one call, one system call, you can populate 3 or 4 pages, right? As opposed to normal read will just give you just one single byte, and you can only populate one buffer. Because at the end of the day, system call, what is the purpose of that? You send it an array that the kernel will read from the data, bring it to the page cache, and all of the way, it will copy it to your user space, right? So this pread v is very critical if you want to populate multiple pages at once, right? And that's why it's being used. That's essentially the improvement. So let's just dive into the details of all of this, and kind of, because it's not as easy as it may sound, you know, because production, it requires heuristics, right? How do I know, right, not to read too much versus read a lot, yeah? So let's jump into it and discuss. Welcome to the Back Engineering Show with your host, Hussein Nasser. And first of all, we're going to start with this idea of combining reads. It's kind of, you can say it's inspired by an existing feature that has been there for many, many years in the kernel itself. You see, the file system, which is a kernel and operating system component, deals with files. And what are files? Really, files are nothing but an array of different size or fixed size blocks. And now when I say block, this is the file system predefined fixed size object, right? And this is where what we store in disk, essentially, and we read from disk. We never, if you read a file and you say, hey, I want only to read, I don't know, HTML, the first header in the HTML, which is 5 bytes. That doesn't happen, you know. You don't get 5 bytes. You always get a whole block. I'm gonna spare the details where the block size is different than the block size in the SSD. Let's assume they are the same, because sometimes they are a little bit bigger, but so assume they are the same, right? So you read with 3 bytes, you get 4 kilobytes. And what happens in the operating system is the operating system start caching that block, so it has a block number, because chances that if you read this, you might need the next 7 bytes, and guess what? I don't need to go to this, because hey, I read the whole 4 kilobytes worth of things, so I'm caching them. And this is beautiful, especially if you have multiple readers from multiple applications, all calling the kernel, all wanting to read something. So they all gonna get through this beautiful page cache. You know, they call it page cache because it is kind of linked to the virtual memory system, and that is a page that is loaded in memory. So they kind of reusing that concept there. Okay, so that's what we have here. So if we read a block, if you read something, you get a whole block worth of it, and it gets cached in the page cache, right? And that's in the kernel, the operating system. So the kernel has a feature saying that, all right, based on your behavior application, I noticed that if you read block 2, most probably you're gonna read block 3 and 4 and 5, right? So what the kernel does is does a read ahead call, and you can configure this in Linux. I'm not sure about Windows. Pretty sure this feature exists in Windows, but you can configure it. Say, hey, I know you asked me to only to read this block. I'm gonna say block right now because you know that when you read a byte, you get a block. You don't get a choice, right? So I'm talking about further blocks ahead of this, right? So since you read block 1, you're going to probably need 2 and 3 and 4. So I'm going to read ahead. Might as well, right? I don't want to ask, because I am making technically another call to the whatever, the driver in this particular case. As a kernel, I'm making a call to the NVMe, right? So I'm making a read to the NVMe saying, hey, start from this particular LBA and read 7 LBAs, right? So instead of reading just 1, I'm just going to say, hey, I know you asked me for 1, right? You asked for 1 byte. You're going to get 4 kilobyte. That's 1 LBA, 1 block, right? But I'm going to read 5. I'm going to read ahead. So this is nice because the next calls that require this, then subsequent blocks, will be satisfied by the page cache ですね. Isn't that cool? So this feature is called read ahead, and you can configure this, especially if you have like database application that kind of nicely always asking for the next and the next and the next. And Postgres takes advantage of read ahead today without even this new feature that I'm talking about, right? It just takes the advantage of the read ahead, so which is nice. Read ahead is a very critical concept. You know, the disadvantage of this, if the kernel miscalculated and read a little bit too much into the page cache and nobody needed that or used that, so now you have a place in memory that is reserved for something that nobody used, which will be kicked in by an LRU algorithm, which will kick out this unused blocks, right? So we're still in the kernel and the page cache. Beautiful, beautiful, beautiful. Now, so this is the read ahead concept in the kernel. So then Postgres said, well, I know read ahead helps when I read a page of 8K, right? And let's go a little bit dive deep into this because we didn't, right? What is a page read, really? What does that mean? So if I read, let's translate it to a SQL, right? So you guys can kind of link these, this daisy chain together. So I am doing a select star from a table. Let's remove any indexes for now. So that's a table, sequential table scan, right? So when I do select star from table, I read as a planner. I read the metadata about the table to find the first page, right? And this first page will tell me that, hey, this page doesn't have to be 1, right? Page 900, right? That's the unique ID of the page. Okay, what does that mean, page 900? It has metadata in the page, which is headers, right? And I can't remember how much Postgres takes headers, because like there's also an overhead for always these 8 kilobyte pages. There is the header in the beginning that tells metadata about this page, like how many rows, what is the first row, what's the position of this first row, what's the position of the last row, a lot of other metadata details. This page need to be translated to an actual read so the kernel can read the actual file. So you need the file name, because guess what? Databases store stuff in files, just like you and I store stuff in Notepad files. Just normal. It's just files because it uses the file system. And there's always I like to talk about, like sometimes I kind of do advanced topics and discussion on Twitter. It's just like, does the database even need a file system? And I think it does not. Right? In Arabic we call it ib. It's an overhead. Yes, it's an overhead for the databases to use a file system. Yeah, you can configure it, but you can essentially just directly read from SSD. There's pros and cons to that because now databases need to understand how to deal with all this stuff. But there is a lot of development of more slim and more I suppose thinner file systems, like such as ZNS, right? ZFS, zone namespace file systems, which uses the zone namespace technology in NVMe. Right? But that's not our topic. Regardless, we read. We issue a read. And I know that, hey, I'm reading this particular page, which is offset 1000 for 8 kilobytes. That's what a read is. You issue a p read. And then, once you do this p read, so we will translate this into a system call, which, if you took my operating system course, you know that there's a cost to that. So you want to, as little as possible, minimize system calls, especially if it is chatty. System call completely shifts. It switches the CPU when it executes your process to something called the kernel mode. And that causes some flushes, some mini context switch, not a full context switch. It flushes whatever you have in register to load kernel information so that it can access the read system call that is in the kernel, right? So it elevates your process to a kernel mode. That's why it's very dangerous to crash in a kernel mode. Everybody saw what happened in CrowdStrike, right? Like once you're in a kernel mode and you crashes, that's it. All bets are off. Corruption can happen, so the system just crashes itself and just blue screens, right? So we switch to a kernel mode, and then we start reading system stuff, right? And then we prevent, of course, the user from reading anything. In that mode, you cannot do anything, but now you have access to the kernel stuff. You start executing all this read code to actually read, which will eventually talk to the block layer, which will eventually talk to the NVMe drive and understand the driver, understand how to talk to the SSD, and does all the APIs, whether NVMe 1.0, we use NVMe spec 2.0. All of this stuff is just baked into the kernel, right? And all is in this p-read operation. So it's costly to do a read. How costly? We're talking microsecond, nanoseconds, right? Not a lot, but adds up. Everything adds up, right? If you turn around and finish this read, you got your data, which now, if we're lucky, the kernel might have read a little bit more and got some stuff, right? But it's not enough, because it might just read one extra block, right? Which is 4K, but the page size in Postgres, it's 8K, so you need a little bit more. Yeah? So then you turn around and says, oh, sequential scan, so we need page 2. Oh, page 2, and I missed all this part, right? Where after you read this page, Postgres, and pretty much any database, puts this page into the shared buffer cache, so that the next time the planner or the user asks for page 1, we hit it from the shared buffer pool. This is user space application memory, not kernel. Now we're in the so there's another caching that's happening in the user space. There's another caching that's happening in the file system page cache, which caches the block size, which is 4K. We're talking Postgres, this is 8K. So one page equal 2 blocks. You can think of it this way. It is this way. You don't have to think about it this way, right? So that's what's happening. So now I'm copying. So that's one thing. You're now having 2 copies of things, right? So you need a little bit more memory for that. But there's no escape for that. You'll have to cache it unless you open the file. And I'm going a little bit deep, very very deep into this topic, but you can open the file with an option called O option _ direct, which means, hey, don't even bother caching this particular file. When you read stuff, just pass it all the way to the app, right? So you can skip that. And MySQL does that. Postgres, I don't know if it does that, to be honest. The documentation not clear, but MySQL says, hey, we do this in particular cases. Right? For certain files, like the wall, we always do O direct. We skip the page cache, right? Which is the operating system file cache. Sweet. All right. So now we did a cache. We did the shared buffer pool, right? Now, if I say, hey, go read page 2, we do a system call, and that's the cost we're talking about here, the double system calls, right? We're doing another system call So that means another kernel mode switch to the CPU, because the process that whatever issued this call, it lives in the CPU. That's the process context, but it needs to be switched to a kernel mode. So now I'm reading. We'll get to the point finally. Right? So now I'm gonna read page 2. I issue that read. So that's a system call. That's the cost. And then we might be lucky, and the file system page cache already cached that stuff. So we have in the page cache. But we might not be lucky, right? And let's say we did O direct, so there is no caching, right? At all in the page cache. Or the p read ahead, we have caching. We have page cache enabled, like a normal read operation, and we didn't get enough read ahead. So some blocks were available in the page cache, some blocks were not available in the file system page cache. So now we need to do another, all the way go to the storage and issue a read, right? An actual physical read tuple from the device. And that's the cost that we're talking about here. And if we can guarantee that, hey, I know that I'm gonna read this page and this page, and I'm gonna probably need 5 other pages, and not only that, the planner knows that, oh, there are other backends, that's what Postgres called them, backend processes that might do reading in the same area. So all right, let's kind of group and negotiate. Let's not do ad hoc stuff. Let's just group. Oh, you want to read? All right, just tell me all what you want, and I'm gonna do one system call. Oh, this backend process requires reading 3 pages. This backend process requires 4 pages from the end. It doesn't have to be sequential. And this backend process needs these 5 pages that are sequential. And they are all sequential as a group, but they in itself they are not sequential. Does that make sense? You know, so each group is sequential, but the whole groups are kind of scattered. You know, so a group of 3 somewhere, and then another group of 5 somewhere, and another group of 6 they are somewhere. Okay, so that's what we do. Right? And then we issue something, a system call that I didn't know about, called preadv, that has a v at the end. But yeah, so that's what's happening, right? A single call, read all this stuff once. So we save on system calls. And this is, the savings is just avoid system calls. Even with epoll, right? Epoll is still very system call-y. It's very chatty, right? Epoll is the ability to kind of read from multiple sockets, right? But it still have very, very, very chatty system calls, which can be costly if you have a lot of, sockets to read from. So that's why we have IO ring, but there's all the drama with the Google that they disabled that for security reasons. Dude, any new product will have security problems, right? Especially if there is eyes for it and there's money. Google was offering money for whoever finds security issues for IO ring. As a result, a lot of people did, and as a result, Google says, this product we're losing a lot of money. Find the security issues, so we'll just disable it. That's lame, Google. But yeah, so IO basically minimizes the number of system calls. Of course, it is an improving a new product that is keep improving. But yeah, that's very interesting, right? So we talked about, what did you talk about? Summarize. We usually send multiple calls. To read each page was its own system call, right? Read a page, go system call. Read a page, go system call. Now we're grouping. And the challenge is how do we group? And there is a whole slide deck that I'm going to reference from the maintainers themselves that tells you these heuristics. How do you pronounce that? Heuristics. Yes, heuristics tells you heuristic. How can we guess? How do you not read too much? Because that's what we're afraid of, right? Because I might read, I see a sequential call, like I'm gonna read page 1, 2, 3. So Postgres will estimate that, oh, you might need 5, 6, and 7. But we're reading it, but maybe the planner will say, oh, actually, never mind, we found what we want. So we stop, and you have caused, as a result, not only amplified read, it's called read amplification, you caused amplified read. So expect that would be Postgres 17, a little bit amplified read, right? And then amplified read ahead at the kernel level. So you need a little bit more bandwidth at the SSD. That might be fine, right? As long as you have enough memory to cache whatever you read, and hopefully you don't have very little shared memory cache, because you don't want to evict pages too soon, right? That has been cached. And I say pages, I mean Postgres database pages in this particular case. So yeah, very, very interesting things. So that's the only challenge that I'm thinking about, right? As how do we prevent overreading, right? So reading these heuristics, can understand when to stop. And that's the challenge, really. Hope you enjoyed this video, and I'm gonna see you in the next one. Again, if you love any of this stuff, check out my my courses. Just go to courses.husseinnasser.com. I go into in depth about all these topics that we discussed in this video, you know, from the first principle all the way to the advanced topics. There are many playlists in this YouTube channel and in this podcast. If you're listening on the podcast, I always talk about these topics as well. So yeah, thank you so much. Appreciate you. I'll see you in the next one. You guys take care.